Okay, today we're going to finish up chemistry by reviewing Unit 2, which was chemical interactions. So this stretched from Halloween of last year up till last week, as far as content-wise. So there's a lot of information here that we'll want to try to parse out, so we'll try to keep it as simple as possible. The majority of what we're looking at is involving molecules. So molecules happen when atoms share valence electrons. Now each atom's bringing one valence electron to the table in this. This is water forming. And you see that oxygen has 6 valence electrons, 2 of which are unpaired. Hydrogen has 1 valence electron each. So what you end up having is that each of the hydrogens shares its valence electron and takes one of the valence electrons of oxygen to create paired valence electrons. And it turns out that if you have 8 valence electrons, you tend to be pretty stable for a lot of atoms that we look at. Now this can happen in 2 ways. You can either have a polar or a non-polar bond. A polar bond is an uneven sharing of the electrons. So in this case, oxygen is more electronegative than hydrogen. So it pulls the electrons towards the oxygen and away from the hydrogen. The result is that you create a partial positive and a partial negative charge on the overall molecule. Okay? So the molecule itself could have partial positive and partial negative charges, and that plays into things like, can you be a solvent, stuff like that. You also have nonpolar bonds. Those are common in your organic molecules, the hydrocarbons, for instance, methane, ethane, propane, butane, those types of things are very nonpolar. So there's just an even sharing between the carbons and the hydrogens. And that kind of leads into that whole concept of oil and water don't mix, right? So reading a molecular formula, if you look at these two, you see a structural formula and a molecular formula. And the molecular formula just tells you what atoms are present. Every atom begins with a capital letter. Okay? So if you look at magnesium sulfate, the capital M, lowercase g, that's one atom, that's magnesium. The capital S is one atom, that's sulfur. And the capital O is another type of atom, that is oxygen. Now the O has a subscript of 4. That means that there's 4 oxygens inside magnesium sulfate. Okay? The subscripts tell you how many atoms of each type you have. Without a number, it's implied that there's 1. So there's 1 magnesium, there's 1 sulfur, but then there's 4 oxygens. Okay? In a chemical reaction, atoms are going to change the partners they share electrons with. So here we have acetic acid and sodium bicarbonate, creating sodium acetate, water, and carbon dioxide. So the atoms are swapping who they're bonded to. And by swapping who I'm bonded to, I change my properties. That's really important. So the properties of the reactants are always different from the properties of the products, because you've changed your partners around. Okay? So what you start with is different than what you end with. Okay? So an example of this that's very visible is if you mix these 2 liquids together, you'd actually form a precipitate. A precipitate is a solid that drops out of a solution. So this particular new compound that they've created in this reaction here is not water soluble. At least not as water soluble as what it was before. So that is a change in my properties because I've changed who I'm bonded to. There's many types of reactions. There's decomposition. That's where things fall apart. So here we see carbonic acid breaking apart into carbon dioxide and water. There's also synthesis, where you're building things up. So you could take calcium and oxygen, build a calcium oxide, where you also have substitution. Substitution, you swap an atom for another atom. So herein we see that AB plus C, we swapped out that A and we formed BC. So you changed who you're bonded to in substitution. Very common with the halogens in OChem. So if you have an halogen substitution on a hydrocarbon chain, that's a really good site to do a substitution chemistry. In fact, there's two types of substitution you can do there that are really, really handy. And finally, you have combustion, which you're probably more familiar with. That's just burning things. So you need some fuel, you need some oxidant, and you react to create new molecules and heat. Combustion is one of those few ones that's always exothermic. We'll talk a little bit more about exothermic, endothermic later, but the other reactions, some of them may be exothermic, some of them may be endothermic. Combustion is always giving off heat. You can see the fire burning off of it, giving off light, radiating that heat. So combustion, always exothermic. Chemical reactions versus physical changes. So there's a big difference here, and I kind of broke it apart for you. So in a chemical reaction, energy is either absorbed or released. So most reactions are either exothermic or endothermic. You're always forming new substances. And the atoms are changing partners. And we see that there are changes to my properties. Okay? Things may fall out of solution and not dissolve as easily. Or you might have a different boiling point, or you might have all these other changes that could occur that are properties of the compounds. Whereas in a physical change, the atoms don't change partners. So water as ice is water as liquid. It's still H2O even if it's steam. Okay? So you're not changing the partners around, you're not creating a new substance. You're simply moving farther apart, moving faster. That's the big difference between chemical changes. We're actually rearranging molecular bonds, whereas a physical change, we're simply just heating something up, making it move faster, move farther apart, become more disorganized, or cooling it down, making it more organized. Now, the main governing concept for reactions is the law of conservation of mass. And that says that matter can neither be created nor destroyed. So what you start with atoms-wise is what you end with atoms-wise. And if you look, here's a nicely balanced equation. We start with 4 hydrogen atoms, 2 oxygen atoms, creates 4 hydrogen atoms, 2 oxygen atoms. Difference is we start out with 2 molecules of molecular hydrogen, a molecule of molecular oxygen, and we created 2 molecules of water. Okay? So in a chemical reaction, the atoms move around, they create new molecules, but the stuff you start with is the stuff you end with. You don't destroy the atoms, you don't create new ones, and that's kind of a key concept for a few things that we're going to do here. The first is to do calculations. So here you see this kind of old school science book drawing here, and they're doing a reaction. They got some sodium chloride down here at the bottom, and in a test tube they got sulfur nitrate. And if you were to dump sulfur nitrate into that sodium chloride, the silver would want to bond with the chloride, and you'd create sodium chloride in a sodium nitrate solution. Okay? And the sodium chloride turns into this white precipitate. Now notice that the scale in the beginning says 300.23 grams. In the end it says 300.23 grams. The way these equations work is that they use the law of conservation of mass that says what you start with is what you end with. And usually they'll ask you what's the weight of one of the missings. So it's kind of a simple algebra problem where you'll have a weight of the reactants and a weight of the products, and one of them's missing. Okay? It's usually a one-step equation. You just subtract off whatever weight is on the same side as your unknown, subtract that off of the weight of the products or reactants depending upon which one you're given, and boom, you're there. Okay? Pretty simple, and it's really using the law of conservation of mass, because the weight that you started with has to be the same weight that you ended with. We can also balance equations. In balancing equations, you want to start with your reaction first off, and then go through and write down a list of each of the atoms present. So in this case, I have carbon, hydrogen, and oxygen. And then go through and count. I have 1 carbon, 4 hydrogens, and 2 oxygens on one side of the reaction, and I have 1 carbon, 2 hydrogens, and 3 oxygens on the other. Now, we know that I can't create or destroy matter, so it must be that the number of hydrogens being 4 on one side, I have to make the hydrogens be 4 on the other side. And I'm going to do that by adding a 2 in front of water. Now by making there be 2 waters, I've increased hydrogens to 4, and I've also increased the oxygens to 4. But now I've thrown things out of whack on the other end. Okay? So I need 2 oxygens on that side. So if I put 2 in front of O2, then oxygens on that side now go to 4. And I can check to see I have 1 carbon on both sides, 4 hydrogens on both sides, 2 oxygens on both sides, and this reaction's now balanced. Okay? So it's kind of a back and forth process. You gotta check one side, check the other side, make sure that everything lines up nicely. So, a lot of what we've been talking about so far is molecules, but there's also ions. Ions are what happens when a atom is so electronegative that it completely steals an electron from another atom. The result is, and you can also steal more than one. The result is an atom that's now become negatively charged, the one who stole, and an atom that's now positively charged because it's lost an electron. And now that you have fully positive and fully negative charges, those 2 charges are going to be attracted to each other. So you're going to actually have ions of different charges want to come together and form ionic bonds. So these are different than covalent bonds because they're the bonds resulting from full charges. It's not simply sharing electrons and kind of this cool coexistence in my valence shell. This is going to create something slightly different. And what ends up happening is that usually these ionic compounds form solids, and they form it by creating a crystal lattice structure. And we saw some of these with our geode process. Okay? So in the geodes, we ended up seeing that the negatives and the positives would all line up nicely, and you would end up growing crystals. And most crystals are, in fact, the repeating patterns of positive and negative ions that we call a crystal lattice structure. Okay? Very, very different looking than molecules for sure. And remember, the big difference is that you've fully taken the electrons here. So it's charges attracted to charges. You're not sharing electrons. Reactions tend to either be exothermic or endothermic. And when we talk about exothermic and endothermic, what we're really saying is energy. So in an exothermic reaction, the reactants have more energy than the products, and they release that energy as heat. Now, if you look at these graphs, what you see is that there's this large peak at first before the reaction starts. That's called the activation energy. Okay? Now, the activation energy is always higher without a catalyst. A catalyst makes it to where a reaction goes faster and starts more simply. So usually using a catalyst, especially in like the body, through a catalyst called enzymes, is very useful. And an exothermic reaction will give out energy to the surroundings, usually as heat. Endothermic, on the other hand, the reactants have less energy to start with than the products. You're actually absorbing energy as heat from the environment, makes everything around it cold. And when the reaction goes, you have the products ending with more energy than the reactants that started it. So that's pretty much all for the basic reactions. So let's talk about acid-base chemistry briefly here. Water can break apart. Just happens. Basically, one water molecule will collide with another molecule, and it will lose a hydrogen to the one water molecule if it hits just right, and you'll end up with creating hydrogen ions and hydroxide ions. In this picture, you see hydronium, which is a bit more of the truth. For right now, just focus on there's hydrogen ions and there's hydroxide ions. Don't worry about H3O positive. That's how it actually happens. But for right now, focus on H positive. Okay? We're creating H positives. I will sometimes call them protons because that's all you would have. If a hydrogen is a proton and an electron. You lose that electron, all you have left is a bare proton. So a lot of times people talk about acid-base chemistry and use the phrase protons. What they really mean is hydrogen ions. Now, there's also chemicals that if I stick into water, it's going to cause water to break apart as well. And depending upon what the concentration of those hydrogen ions is after I add these things to the water, we call it acidic or basic, acids and bases. So on the pH scale, the pH scale is a logarithmic scale. We saw some of these a little bit in one of our tests. But a log scale makes it to where you have these numbers, and it's just 0 through 14. Okay, a lot easier than talk about 10 to the negative 14, which is why we use logs. So a strong acid is defined as anything up there in the 0, 1, 2 range. You're strongly acidic. Things like battery acid, acid rain, lemon juice, stuff like that. They're all down there. Vinegar. Weak acids, getting a little bit closer to 7. Okay, so if I'm in that 4, 5, 6 range, I'm probably a weak acid. If I'm in that 0, 1, 2 kind of range, I'm a strong acid. Okay, same thing for weak bases, baking soda and seawater, stuff like that. 8, 9, 10s, not really strong bases, but by the time you get to lye and ammonia, that's much more strong base. A pH of 7 is considered neutral. A pH below 7, so 0 to 6, is acidic. And above 7, so 8 to 14, is considered basic. Okay, so you have acidic, neutral, basic. Acids in general taste sour. They have a pH less than 7. They're going to turn blue litmus red. That one's pretty important to remember. And they react with metals to produce hydrogen. Act with active metals. Whereas bases don't react with metals at all. They taste bitter. They have a pH greater than 7. They turn red litmus blue. And they also feel very slippery. Okay? Carbon has 4 valence electrons. And because it has 4 valence electrons, it can make 4 bonds. Okay? So we can see that when it makes these bonds, it makes them in a variety of ways. So we have 2 molecules here. We have butane and isobutane. Isobutane is a branched chain of regular butane. Okay? And if you notice and you look at these pictures, every single carbon has 4 lines coming up, and each of those lines represents a bond. Okay? Carbon always makes 4 bonds. And it does this because carbon has 4 valence electrons. Now, when you're making organic molecules, you could do what's called a polymerization. And when you polymerize, you literally repeat a small organic molecule over and over and over again to build up a gargantuan chain of a molecule. And we call the small starting material monomers, and the big material a polymer. Common polymers are plastics, but there's natural and synthetic ones. So synthetic things like plastics and nylons and stuff like that are man-made. Polymers, where we take small molecules and reproduce them over and over and over again, link them up, and create these polymerizations. However, there are natural ones too, and those natural polymers generally play a pretty important role in the body. Okay? Now, before we talk about those natural polymers, one thing you should remember is that carbon is in all living things. So cats, plants, fungus, people, everybody. All carbon-based life, it uses carbon. Okay? Now, the reason is that it can share bonds with itself and other elements easily. It shares electrons, and it can form bonds in all kinds of crazy different ways. Straight chains, branch chains, rings, stuff like that. Now, the 6 main elements that you gotta know for living things are chnops, otherwise known as ponchos. That's carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Okay? You must know ponchos. And ponchos is what makes these large, naturally occurring polymers. So our first one we'll talk about is DNA, nucleic acids, to be specific. Nucleic acids are polymers of nucleotides. Okay? That's your ATCG. Now, ATCG creates this repeating pattern that literally determines the differences in living things. So DNA is extraordinarily important for us. Proteins, on the other hand, are more of the doers in the body. They're, when taken in as a nutrient, they're what we use to build and repair body parts, and they're a polymer of amino acids. So again, it's a naturally occurring polymer. In this case, there's 20 different monomers that are going to combine together to create all these different proteins, enzymes, which are biological catalysts, stuff like that. Whenever the body wants to do something, it makes a protein. Next up, you got carbohydrates. Now, this is glucose pictured here, and you notice how it does have kind of a repeating pattern, but those hydroxyl groups, the OHs, they're flipping around a little bit, and those subtle differences create huge differences in sugars. So you end up with things like glucose and galactose and all this kind of stuff. Now, a simple sugar is one like glucose. You also have a complex sugar where we actually have multiple sugars bonded together, like lactose does. And finally, we have lipids. Energy-wise, gram for gram, lipids are the most energy storing. This is fats. This is triglycerides, oils, cholesterol. All these things are different lipids. And that's about it for our test. Definitely watch this video more than once. This is all the material that you need to know for the exam. So if you memorize this material, if you take notes on it, if you do something with it, hopefully you'll do very well on our test. So have a great day and get to studying.